Hello, everyone. On our neck journey, I just wanted to talk a little bit about origin and derivation of the guitar neck. So we're pretty sure that most stringed instruments have necks. And perhaps the first neck was a hunter's bow stuck on a gourd or something to amplify the sound. Maybe that was the first stringed instrument. We'll never know, of course. But I've been trying to think of a guitar that doesn't have a neck, and I can't really think of one except for maybe the pedal steel guitar or lap steel guitar, which was pointed out to me by our soulful cameraman Ryan, is basically all neck. So anyway, guitars have necks, and they started out being pretty rudimentary. The instruments that preceded guitars didn't have frets, so necks were quite simple things with a smooth surface that the player could press the strings down to and play. Without frets, then the lute and other instruments of its time came with frets that were tied, basically strings wrapped around the neck to form frets. And then finally, metal frets applied in a variety of ways, usually pounded into slots in a fretboard like this one. The neck was kind of defined in the mid-1900s by Spanish builders led by Antonio Torres. And that kind of neck shape has not changed very much. I think that modern players would not be surprised by the size and shape and feel of necks that were made in the 1850s, say, in Spain. And guitars actually date back quite a bit before that. It's interesting to know that Antonio Stradivari built guitars that are generally considered excellent instruments now. And here are some YouTube clips of one of them, a couple of performances by wonderful players showcasing this interesting instrument. And this isn't a 6-string guitar. This instrument has, what would it be, 9 strings, 5 courses, 4 double strings, and then a single string on top, kind of like the 12-string guitar has double strings. This is a 5-course guitar by Stradivari. So hope you enjoy listening to this. Now, the neck didn't change very much until the strings changed. And this is a big, big change in terms of the requirements of the neck and what the neck needed to do. So sometime around 1900, sort of, steel strings of high quality were available and were fitted to musical instruments that were played with a plectrum or the fingers, like mandolins, banjos, and guitars. So those strings are made of music wire, which is kind of a refined alloy of steel, still available today. And the very fact that it's known commercially as music wire is evidence that there was a great need for this stuff, and people really wanted there to be good music wire. And many, many people have adopted steel strings since then, as we all know. Most of us play steel strings to this day. And one of the big differences between the intestine gut, so-called gut strings, which then were supplanted by nylon strings around World War II, the big difference in steel strings is the tension. So whereas high-tension nylon strings are maybe 85 pounds total force, compression force on the instrument, steel strings are probably around twice that force, depending on the gauge. A set of 12s that I use on my guitars, for example, exerts about 165 pounds of force when tuned to concert pitch. So that's quite a big change. And when we kind of double the load on the neck, we can expect that the neck is going to respond, sometimes in ways that make the guitar suffer as a result. One thing that you can do to help make the guitar not distort is to make the neck big. And here's an example of mahogany neck, probably from, I don't know, maybe 1910 or something like that. This is a Ditson brand guitar made by who knows who for a trading company called Ditson, which was a big retailer in the United States 125 years ago. This is a nice shaped neck with a V. So there's a spine, in other words, down the back of the neck. And this one is about an inch thick here at the 9th fret. Not too big, but not really, really big. And then here's my happy Gibson L3 from 1918, and measuring at the same point here at the 9th fret, this is 1.350 inches thick, which is pretty big. It's 35 millimeters. And a pretty substantial neck. A lot of people would call this kind of neck a baseball bat neck due to its large volume. And I'm pretty sure that we can say that most people would not prefer a neck that felt like this. This would be more comfortable, and even more comfortable than that, a modern neck shape where this is maybe 15 or so percent smaller in thickness than an old mahogany neck like this. In order to get the neck to behave properly with this increased string tension, the truss rod was applied in 1923. A genius who worked at Gibson named Thaddeus McHugh designed the truss rod and also at the same time designed the screw height adjustable bridge for the archtop guitar. And as of 1923, Gibson Company was granted that patent and was able to put adjustable truss rods in their necks and therefore achieve two important goals. One of them was the fact that the neck could be made smaller in cross-section and more comfortable for people to play because the neck was the right shape for most people's hands. And the other one was, and this is mentioned in Ted's patent, the truss rod allowed the company to use wood which would otherwise not be suitable for guitar necks. And the only conclusion I can come to is that that means curly maple, because they had access to really good local maple in Michigan, and some of it, of course, is curly, because some of maple is always curly. And because of the violin family instruments that they were said to be emulating, people expect curly maple on premium instruments. Before the adjustable truss rod, there were a variety of schemes to reinforce the neck employed by different builders. Let's have a look at Frank Ford's page, where he helpfully explains and photographs a variety of methods that the Martin Guitar Company used to reinforce their mahogany necks, starting with no reinforcement and then adding a little strip of ebony down the center, right underneath the fretboard, adding a T-shaped bar that they used for several decades of steel, T-shaped in cross-section, and then a hollow square tube which replaced the T-bar. And then finally, Martin bit the bullet and went to an adjustable truss rod that's accessible through the sound hole. There have always been ways of trying to reinforce the neck without an adjustable truss rod, and we're going to touch on one more, primarily centered around carbon fiber. So there are several ways of creating a carbon fiber structure that can be added to a wooden neck to helpfully support it. And one of the ways of making such a structure is the manufacturing process called pultrusion. So pultrusion, partly pulling, partly extrusion. Basically, the fibers that you're using come off a spool. They're drawn through a bath of resin. and then they're pulled through a long die with heaters in it, and the resin is heated and the material is constrained by the internal shape of the die and comes out with a perfect cross-section that doesn't vary at all in the length of the part. It's a very, very high-speed, efficient process. This stuff gets made by the mile, lickety-split. And here I'm showing you this. I don't have a piece of carbon pultruded stuff at hand, but I'm showing you this. This is a product that we can use to keep the plow from tearing up our flower beds when it snows, at least where I live. Anyhow, pultrusion is a cool way of making a long piece of steady cross-section reinforcing material, but it has a little bit of a drawback in that you can't use the resin that you would most like to use. In other words, epoxy resins have a wide variety of chemistries and chemical properties when they're made, and when they're cured, they have a pretty wide variety of mechanical properties. And obviously for our work, making a precious guitar neck as best we can, we would opt for the highest quality, highest stiffness epoxy resins. Unfortunately, they don't apply well to the pultrusion process. There are pultruded carbon products from a variety of vendors. You can do your own testing to see which one you like. Also, let me suggest that you have a look at this link, which shows how I installed a new kind of neck reinforcing system that is also not an adjustable system in an old Epiphone guitar, replacing the dysfunctional, non-working truss rod that was supplied in the guitar when it was built in the 50s. I forgot what year, but at any rate, the truss rod wasn't working and the neck was a mess. And I was able to replace the fingerboard with with a fingerboard with the frets in the right place. That was important so that the guitar would play in tune. And added this D-Tube, so-called D-Tube, made by Dragon Plate or All Red and Associates, a manufacturer of composite structures in New York State. And these folks do a fantastic job. They've done wonderful engineering and have come up with an excellent series of products if you choose to make a guitar with a non-adjustable reinforcing system. It's something that you should seriously consider. The way it works is that the structure itself is way stiffer than the wood it replaces, and it's also lighter than the wood that needs to be removed in order to install it. So a couple of big benefits for those of us who are trying to make stiff, light necks. Okay, so I think that that's probably the highest embodiment of a non-adjustable truss rod-like reinforcement. Again, no adjustment, but you get the benefit of a very efficient structure that's improving the properties of a regular wooden neck. To orient you in what we're going to explore, here's a neck that I'm making with a process that I've developed and that I like so much. And this is also a kind of a D-shaped reinforcement. You can see there's a neck core material, a vertical grain Douglas fir, and then I think you can see this black material is the end of carbon fibers, the same fibers that make this post. We'll get into the weeds and I'll show you exactly how that works. But in the meantime, just conceptually, let's notice that this itself is a D-shaped reinforcing scheme. And the carbon is pretty close to the outside of the neck. There's just a little skin of veneer on the back of the on the back of the neck to hide the carbon fiber, and which means that the carbon fiber is positioned as best as it can be to support those loads and resist bending and resist torsional or twisting loads. Just to round it all up, Thaddeus McHugh invented and gave us the adjustable truss rod, which, oh, here's one. There's one. And there's one. These rods have served us well for many decades now, and this was really a coup for the Gibson Company, who was able to make a slender, modern guitar neck and be able to stand behind it from a service point of view. Their patent was granted in 1923, and it remained in force until 1940. So other guitar companies, if they wanted to try an adjustable truss rod in their neck, had to figure out how to design something that did not violate Gibson's patent protection. And the problem for those manufacturers was that Thaddeus McHugh devised the simplest, cheapest, lightest, and most effective truss rod that we have today, or that I think could ever be invented, which is simply a compressional rod. In other words, the same way that the strings exert a force on the front of the neck, the truss rod exerts a force on the back of the neck, being positioned where it is. Let's look at how the truss rod works, and we're going to examine the original design by Ted McHugh. And again, we're going to use my favorite example of a diving board. So here's a diving board with somebody standing on it over here, exerting a force in this direction. So the top of the diving board is getting stretched. That's called tension. The bottom of the diving board is being compressed, which is called compression. So this is being shortened on the bottom and lengthened on the top, right? A little thought will indicate that there's some place somewhere near the middle. We don't know exactly where it is. It depends on the physical properties of the diving board. But there's some place in between the stretching side and the crushing side where neither of those things are happening. It just stands to reason. And we're going to call this place the neutral plane. And the neutral plane, we see that we only have bending. We don't have tension, and we don't have compression. And this is a really important thing in guitar neck design. So if here's our fingerboard glue joint, and neck. So somewhere in here, we have a neutral plane. On this side, we've got 6 strings that are trying to pull the neck forward. And Thaddeus McHugh designed a rod that can be thought of as an unbreakable string that's on the other side of this neutral plane. And this is the key to how this works. Whereas the strings are trying to bow the neck forward, the truss rod, when it's tuned with its adjustable nut, tries to drive the neck in the opposite direction. And that's using the physical properties of the neck material that we already have. In other words, wood is already excellent in compression. And especially this fingerboard material that we're using, whatever this is, normally it's a tropical hardwood like rosewood or ebony, is really good in compression. So that means that we can depend on the fingerboard not to get shorter when we tighten the truss rod. When we tighten the truss rod, it shortens the back of the neck. And that's how it works. It crushes the back of the neck, just like the force applied to this beam crushes the back or the underside of the diving board. I hope that's clear. For my money, this is a better design than any of the double rod designs, where in the double rod designs, in one way or another, there's one element that's made of metal and then another element made of metal with threads on it and some kind of nut that bears on this. And the idea is that this element will not change length and that this element will get shorter when you tighten this, and so it'll end up curving in this direction. My feeling is that this compressive element, this extra piece of metal, which would need to be here somewhere, is redundant. It doubles the weight of the rod, and it means you're not using this beautiful piece of fingerboard material as a compression element, which already exists. You already paid for it. You already install it. You need it anyway. Why not use its attributes as a compressive member and allow the rod to apply tension on the other side of the neutral plane? That's the end of my truss rod sermon. And so I believe that the compression rod, the simple original Gibson compression rod, is the best possible design for a truss rod. One man's opinion.